Now that we know how to generate an alternating EMF, we're going to look at how we actually measure the voltage or the current of an EMF that is alternating. And it's a bit of a tricky situation, given that measuring current or voltage of an alternating source is somewhat difficult. And the reason for that is that as the current or the EMF or the voltage is going to be constantly changing over the cycle. And what I mean by that is that if we consider, say, we'll just start off with current to begin with. If we look at a current versus time graph, what we would see is that it follows a sine wave pattern. So if you wanted to state what the current was that was being produced, you'd either need to state, say, the maximum or an average or some representative value, given that over time the current will actually change quite a bit. So the two problems that we have there, the two most significant ones obviously, if you were to state the maximum, the problem with that measurement is that the maximum is only reached once per cycle. So to state what the maximum is, it's getting to that value, but it's not a very good indicative value. The second problem is that the average over that cycle is going to be 0. So neither of those two measures are particularly useful, given that they're not good representative values of the quantity that you're interested in. So there's another way that we can do that though, and it's a little bit could be a little bit tricky to make sense of, but hopefully we'll be able to step through it. So in order to determine an appropriate measure, we need to use the power that's going to be produced. And the reason why we use power is to do with the equation that links power to voltage, current and resistance. And what I mean by that is that if we look at the equation, again we'll deal with current, and there is a similar sort of derivation for voltage. As we've seen in Unit 5, the power across a resistor is equal to I squared R. So if we take that previous graph that we had of the current versus time and we convert it to power versus time, first of all of the negative values, when you square them, will become positives. Secondly, we end up with two maximums per cycle because the negative value squares, and so it ends up as a maximum power. So that would represent the same time frame as the graph that we saw above. You can see there it's a sine squared function is the shape of that curve, considering that the I function, or the function of I with respect to time, was a sine wave. So there's our power, and it's now positive, so we can do something there to state what something about the current itself. So with AC values, so whether it's a current or a voltage, they are stated in terms of the equivalent DC. Sorry, so the equivalent DC value, so direct current value, and more specifically sort of a flat direct current value that would deliver the same power as over one cycle. So in this case, if you were to think about summing up all the values for the power here, you could go through and determine what they are and add them all up over the cycle that's shown there. For a DC value, what that turns out to be is the average value. So this is the average power over one cycle. So basically we're going to use this this power here is the same as the total over the cycle, and that means that we can then work backwards to figure out what the power would be. Sorry, not the power, what the current would be based on that average power. So if we go back to our equation for power, P equals I squared R, in this case we now need to figure out what the power is across here and how it relates to this maximum power. So the maximum power here is related to the maximum current, but we only want half of that power. So we could say that for the AC, we could say that it's I max squared times R, but that would give us the peak of that graph, so we need to find half of that, so half of I max squared multiplied by R. And we've already said that we want to express that in terms of an equivalent DC component, so we're going to call this one IDC. So that would give us the current that would be related to that pink line that we've got on that graph there showing the average power. Now we can then figure out what that IDC value would be. So that means that we could say that IDC squared is going to be equal to half of the maximum of the AC cycle squared, given that the R terms here will cancel. And so taking that a bit further and just a bit of algebra, we would then find the square root of that, so half of I max squared. And again, a bit more algebra, we can show that that equivalent DC current would then be I max, so the square root of I max squared is just I max, divided by the square root of 2. So now we've got a value there that we can use a little bit more meaningfully with AC, but instead of referring to a DC, we're going to call it a quantity that relates to the AC current, and that value is actually known as the root mean squared value. So RMS is the term that we're going to use here. So the RMS value for the current of an AC cycle is simply the maximum current, so I max over the square root of 2. So that's how we define the current that's being provided by an AC source. We look at the RMS value instead. The same process there can be followed for voltages, and you'll remember hopefully that power is equal to V squared on R, so similar sort of thing can be done for voltages. I won't show the derivation here, but if you do want to have a look at it, let me know and I can go through it with you. And we get that the RMS value for the voltage is equal to V max over root 2. And again, that's another equation that's in the data booklet. Now, just to this idea of root mean squared, if you think about the process that we went through, the first thing that we did is to square I. So you can see here that we squared I. We then found the average by basically taking this factor of a half, and then we worked backwards again and found the square root there. So that RMS is basically just explaining the process that has been conducted in order to get to a representative value for the current itself. If we compare some of those AC quantities to their DC equivalents, so we're going to look at some of the equations that we already know for DC and then have a look at how they compare to AC. So the resistance in DC is equal to the voltage divided by the current. For AC, we then have that R is equal to the maximum voltage divided by the maximum current. Now, the the data booklet here uses a slightly different notation, so I'm just going to change that to match. Instead of the maximum, they just refer to the naught value. So V naught on I naught is the maximum, and that's also going to be the same as the RMS value divided by the RMS value for current. So that is another equation that you'll find in the data booklet, that one there. So looking at the resistance in an AC sense. Likewise, if we look at an alternative for power, so we know that power is equal to voltage times current in DC. Couple of different representations here. So the maximum power would be equal to the maximum current multiplied by the maximum voltage. And so there's another one that's in the data booklet. And finally, if we then look at the RMS values, so we could just say that it's V RMS multiplied by I RMS, so multiply the two RMS values together, which we know that the RMS value is V max over root 2, and the I RMS value is I max over root 2, and I should change that again to represent the way that it is in the data booklet, being I naught and V naught. If we then multiply the two root 2's together, we get that root 2 times root 2 is 2, root 2 squared is 2, and so we end up with the equation that the power is also equal to half of the maximum times maximum voltage times maximum current. So notice that that's the power that's being generated over the cycle, whereas the equation before was the maximum power that is produced. We'll have a look at a few questions in class that deal with these concepts, so you can sort of get a better sense of where to use these equations and why the RMS values are important quantities to have a good understanding of.